The Ryzen 9 efficiency is driven by 4 key pillars in the Zen 3 instruction cycle. First, it has continuous processing loop. A unified 8-core CCX with a shared 16 megabyte LT cache allows all cores to access data simultaneously, eliminating communication bottlenecks. Second, high efficiency pipelining. The micro operation cache streamlines the path for instructions, minimizing the need to repeatedly decode complex code. Third, predictive intelligence. Ad- advanced branch prediction accurately anticipates program paths, preventing costly pipeline stalls. Finally, the out-of-order execution. An aggressive execution engine with dual 256-bit FMA units maximize instruction per clock, or called IPC. It's delivered desktop class power in a mobile format. Dua, tiga. So understand Zen 3. Think of it as a high-speed assembly line divided into 3 main zones: the front end, the dispatcher, and the execution engines. The front end. This is the preparation phase. The CPU predicts what data it needs, pull it from the instruction cache, and decode it into small, manageable tasks called OPS or OPS. Next, the dispatcher. Think of this as the traffic controller. It takes those tasks and directs them to the correct lane, either the integer side for the basic logic or the floating point side for complex math. The final phase, the execution engine, the back end. This is where the actual work happens. A series of specialized units, ALUs and HGUs, crunch the numbers and instantly store the result back into the data cache. In short, we fetch it, we organize it, and we execute it. Now, let's dive into the specifics of each stage. This slide focuses on the instruction fetch phase, also known as the front end of the pipeline. This is the predictive stage of the processor where the goal is to keep the execution units constantly fed with data. First, the front end process. The predictive start. The process begins with branch prediction with guesses the next address to prevent the pipeline from stalling. Next, data table. It fetches up to 32 bytes of data per cycle from the 32 kilobyte L1 instruction cache. The third one, pre-decode logic, scans raw bytes to find instruction boundaries and attach metadata for further processing. Next, latency management. If the required data isn't in the L1, in L1 cache, the system proactively pulls from L2, L3 cache to avoid delays. In short, this stage is about speed and accuracy, predicting what next and prepping it for dispatch. We are still in the front end. After the data has been received, it must be translated. It convert complex X86 instructions into simple micro-ops operation, or called micro-ops, that the hardware can execute. The throughput can decode up to 4 instructions per cycle. Simple task is equal to 1 micro-op. Complex task is equal to multiple micro-ops. When it stores already decoded micro-ops for loop or repeated code, the CPU skips decoding entirely to save power and time, meaning to promote efficiency. Next, the handover. It decodes micro-ops are queued for register renaming, preparing them for the out-of-order execution engine. Finally, the micro-ops enters the execution stage, which is split into 2 specialized departments: the integer engine for basic math and floating point engine for complex decimal and multimedia. This is where the out-of-order magic happens. A dynamic scheduler. The scheduler picks micro-ops from the queue based on the readiness, not the original order. If a call waiting waiting for data, it skip ahead to work on the independent task. A dynamic scheduler picks tasks from the queue based on readiness and not their original order. If one task is waiting on slow RAM, the scheduler simply skip it to work on other independent tasks. The Zen 3 has multiple lanes or call ports. It can start up to 10 operation per cycle in the integer engine alone. The reorder buffer are all called ROB, a massive 256 entry log that keep tracks of all in-flight instructions, ensuring they eventually finish in correct order. Everything is kept in check by the 256 entry reorder buffer, which ensure that even though the tasks were finished out of order, they are retired and completed in the correct sequence. Now the jumble or the out of order. Once instructions are turned into micro-ops and dispatched, they enter the issue queues and schedules. This is where the order breaks. If instruction 1, waiting for data from slow RAM, the schedule skip it. It look at instruction 2, 3, and 4 if they are ready, then it executes them immediately. The memory access and cache iteration. The final stage is managing the data itself through the load store unit. It uses address generation units AGUs to calculate exactly where data is located in memory. The CPU follows a search chain through the cache hierarchy, starting at the fast 32 kilobyte L1 data cache, moving to 512 kilobyte L2, and finally the shared L3 cache. If all cache miss, it must access external DRAM. To keep things moving, store buffering allows the CPU to save data to a temporary buffer first, so it can move on the next task without waiting for slow memory writes to finish. The finish line, write back, and retirement. In the final stage, results are stored temporarily in a massive 256 and 3 reorder buffer ROB, while instructions are executed off order. They are retired strictly in their original program order to ensure the software sees a perfect logical sequence. Once the ROB confirms the execution was correct and no branch misprediction occurred, the results are permanently committed to the registers and cache if an error is found. The ROB act as a safety valve, discarding the wrong instruction and restarting from the last known correct point. RIZMAN 9 5900 X is more than just a spec bomb. It's a masterclass in microarchitecture efficiency. By unifying the core complex and doubling the accessible L3 cache, AMD moved beyond raw speed to solve the fundamental latency issue of mobile computing. The transition to an 8-core CCX was transformative. By removing the internal barriers between cores, AMD eliminated inter-core combination bottlenecks, allowing for a much more fluid data flow. Second, we see a massive leap in efficiency by combining the 7 nanometers manufacturing process with Zen 3's IPC gains. The chip delivers desktop level power while operating within a strict 45-watt mobile envelope. Finally, this architecture leaves a lasting legacy. It has set the blueprint for modern, high performance, high efficiency mobile system on chip, proving that thin and light form factors can still handle the world's most demanding workloads. That's all from us. Thank you very much.